Hello everybody, welcome here to another video by JFB, and in this video we are going to be looking at the NOR gate. So without wasting much time, let's get started. The NOR gate is just another type of logic gate, but for it's a little bit complex. And what do I mean by complex? It's not just a single type of logic gate, it's actually made up of two of the basic type of logic gates. If you don't remember what the basic type of logic gates are, we have first of all the AND gate, then we have the NOT gate, and finally we have the OR gate. So the NOR gate is just a combination of the basic type of logic gates. Now, which logic gates are those? Well, it's only made up of two of the basic logic gates, and as you might guess, telling from its name, NOR gate. So it stands NOR gate, NOR gate. You can actually split this up. This N is representing the NOT gate, and this O is representing the OR gate. So the NOR gate is made up of the NOT gate and the OR gate. And if you remember, the diagrammatic representation of the NOT gate is simply a triangle like that, circle in front, an output line, and an input line. That's the NOT gate. Then the diagrammatic representation of the OR gate is different. You have a curvature at the end, then something like that, an output line, then two input lines. Now, how is the NOR gate made from a NOT gate and an OR gate? How is it made? How can you connect these two so that you make a NOR gate? The NOR gate is made by feeding the output of the OR gate into the input of the NOT gate. Let me show you what I mean. So we can connect an OR gate, then we connect this OR gate to a NOT gate. So we transfer this NOT gate over there to feed the output of the OR gate into the NOT gate. So we connect the NOT gate here and its output there. So whatever inputs you give to the OR gate, the output of the OR gate will be fed into the input of the NOT gate. I know it sounds a little bit confusing, but stick along with me. So it's simple. The output of the OR gate is the input for the NOT gate. That's all. So just think of the NOR gate as a combination of these two, an OR gate and a NOT gate, where the NOT gate is the one actually giving the output, but its input is coming from the OR gate. The NOR gate has its own diagrammatic representation, and it's quite easy. You're just trying to combine these two diagrammatic representations. So we only get the circle from the NOT gate and this curved back end from the OR gate. So we draw the curved back end, then we get the circle from the NOT gate, and there you have it. This, my friends, is a NOR gate. That's all. So all this here is represented by this here. That's all. All that is represented by that. And what's happening? You are feeding the input into the OR gate, and the output will be fed into the NOT gate. So now let's draw the truth table of the NOR gate. And if you don't know what a truth table is, the truth table is simply a table whereby we track the inputs which we give to the NOR gate, and we also track the outputs the NOR gate gives us. Let me draw a NOR gate. So there we have a NOR gate, then circle in front here, and like that. We can label the input lines using letters and the output lines using letters so that we can easily track it on the truth table. So we can label this input line as A, label this input line as B, and label this output line as C. Then we can draw a truth table. If you've watched my previous video on the NAND gate, whereby the NAND gate is just a combination of the NOT gate and the AND gate, I said you can use a formula 2 power x to determine the number of rows that your truth table has. This 2 power x, or the x in short, is coming from the number of input lines you have. So you have 2 input lines. So you can say 2 to the power 2, which is equal to 4. This means you have to draw 4 rows on your truth table. That's all. And how many rows do I have here? 1, 2, 3, and 4. So that's enough. Then we can split the truth table along these lines, whereby these will be the input, and finally we'll have the output. Then we can place the letters finally, A, B, and C. Now that we have that, let's now just track the inputs. So we're going to start first of all with an input of 0 on A and an input of 0 on B. If you've never used the NOR gate before, or this is your first time learning the NOR gate, To figure out what its output on C will be, it's quite easy. You can just break it down into its simpler components. So you join OR gate there, then feed the output of the OR gate into the NOT gate. That's all. And easily track what the output would be on this line. So this can be your A here, and this can be your B there, and this can finally be your C. So now, with an input of 0 on A and an input of 0 on B, what do you think the output will be on C? So now let's solve this. So we have 0 here and 0 there. Whenever you have zeros on both sides of the OR gate, there's no 1, and the OR gate, for it to give you an output of 1, you have to have 1 on either of its input lines. So you don't have an input line which has 1, and that means the OR gate will produce an output of 0. This output of 0 will be given to the NOT gate as an input, and the output of the NOT gate will be a 1. So you're simply feeding the 0 which was produced from the OR gate into the NOT gate. That's all. So when you put 0, 0 on A and B, the OR gate produces a 0, and that 0 is fed into the NOT gate, and the NOT gate takes that 0 as an input, and that 0 is the 1 which you have on C, because every time you give a NOT gate a 0, it gives you an output of 1. Now what about 1, 0? So 1, 0, 1 on A, 0 on B. What do you think the output of the OR gate will be? And since this time you have given the OR gate an input of 1, it will produce an output of 1. So it will produce an output of 1 here. That output of 1 will be fed into the NOT gate, and whenever you give the NOT gate an input of 1, it always produces an output of 0. So you have a 0 there. What about a 0 on A but a 1 on B? So 0 on A, 1 on B. And again, this time the OR gate will also produce a 1 again, because every time you give an OR gate a 1, it always produces a 1. That 1 will be fed into the NOT gate, and the NOT gate will simply produce a 0. That 0 is your output, and you write it there. What about 1, 1? So both input lines are 1, and again, every time you give an OR gate an input of 1, it always produces an output of 1. This 1 will be fed into the NOT gate. The NOT gate will produce an output of 0, because every time you give a NOT gate an input of 1, it always produces 0. So you write 0. So that, my friends, is the conclusion of the truth table for the NOR gate. We have successfully tracked all of its inputs, all the case scenarios. We have 0, 0, 1, 0, 0, 1, and 1, 1. And we have produced all its outputs.